Hi, welcome to the Earth Science Classroom, the channel devoted to Earth science topics and videos. So today we're looking at plate tectonics, looking at convergent plate boundaries and the classic ocean to continental convergence. So the ocean crust smashing into the continental crust and what happens. And we're going to look at how we draw the diagram, explain the processes and all the features that are associated with this kind of boundary. And this is what will be covered in the video. So we'll look at the annotation of the diagram. We'll show the processes, for example, like subduction, convection currents in the asthenosphere, and that will lead to volcanism and magma production from the slab subducting. Look at metamorphism, look at how the slab is actually going to descend into the asthenosphere and the different variations of how far it goes in the Earth's interior. We'll look at the ocean trench that is created because of subduction. We'll look at the volcanoes that are created on the surface of the continent and a certain range from the subduction zone to where the volcanoes occur and the kind of magma we get from this, and also the accretional wedge and prism that works there, and the magma kind of magma flow that is generated from different types of dip angle of the subducting slab. So that'll be the video, and guys, let's jump right into it. So first, let's back up a little bit on the plate boundary. So again, boundary is when two plates meet. And a plate is the crust and lithosphere combined as part of the upper mantle. And then obviously the moho is going to separate the crust from the rest of the mantle. All right. And then convergent means to come together. So the two plates are going to come together, collide, move towards each other, and something's going to happen right here when they meet. And so we're going to discuss the ocean crust meeting the continental crust. And what's going to happen with these two different plates meeting. So I've drawn this basic diagram here where I've got these two plates meeting, the black plate on the left and the green plate on the right. So the green plate would be our continental plate. And the black one would be the oceanic plate. And we can start to add in some details. So it'll be symmetrical in terms of the layers. So this part here would be our crust. And this part here would be our lithosphere. And together it would be the plate, as discussed earlier. And then below it, you would have the asthenosphere. And if you want to go in more detail, you can add in things like the moho, which will be here, the bottom part, deepest part of the crust. Also, you can add in the lithosphere, extends down to roughly 100 kilometers, but this is general, but under the oceans, it could go down as 35, even 25, depends on the ocean crust. So as deep as that, but generally the lithosphere is 5 to 7 kilometers thick under the ocean. So this is the extreme depth, which really should be over here under the continents, right there, extreme depth. But again, the continents are on average around 25 to 35 kilometers thick. So they're a lot thicker than the oceans, as shown by the scale and diagram. And you have to draw that because you want to show the difference in the size of the two different plates when they meet. So the asthenosphere really extends from the average 100 down to about 660 kilometers, and some can argue only 410, but for this we can do both. But this is where we have our convection currents. Again, I've done a video on these exact layers, both the crust, lithosphere, upper mantle, and asthenosphere, so check those out. That'd be great. And the convection currents are going to be actively moving the above solid plate. And you want to draw the arrows going towards the green or towards each other, as it is a convergent plate boundary, okay? And you want to show that the plate is being moved by the asthenospheric convection current, so the arrows will be the same direction. And the same thing on the other side. So this is our crust. This is our crust right here. All right, and it's a lot thicker as discussed. Okay, here is my moho. I'll do that in red. There we go. This is my lithosphere. I'll just put a little L for lithosphere and A for asthenosphere. And you can draw the arrows going towards like this. All right. So you show convergence by the direction of the arrows, because the arrows and the convection currents are dictating the direction of the above plate, whether it's continental or oceanic, and that would create the kind of plate boundary. We have three. We have our transform, divergent, and in this case, we're going to convergent. Now, there are three types convergent because there's two types of plates. So you do have ocean continental, you do have ocean meeting ocean, and continent meeting continent. Well, for this sake, we're just going to do our ocean continental, the classic one. Okay, so we have some details there. You can go even further. You can. I put in this little layer here to show sediments and sedimentary rock. We can get to that later on when we get to our subduction. Now, why have I put it on the ocean crust rather than continental crust? Well, obviously the top layer of continental crust would be mostly sedimentary, but for this purpose, you want to show that it's kind of a thick igneous rock, and the igneous rock with the ocean plates is a lot thinner, but the sedimentary rock will form mostly in the ocean environment, whereas the sedimentary rock on the continents is it's basically being transported towards the coastline and the margin of the continents where it meets the ocean. Okay, so let's get on to density. All right, density is a huge thing with this diagram, or with plate boundaries in general. Density. Which one is dense? Which one is less dense? Okay. Try and stay away from the heavy and light reference or words. It's not really accurate. Use the word dense and less dense, or more dense. Okay. Now, density again is mass over volume, so it's the amount of weight or mass with gravity in a certain area of volume. Okay. So again, drawing the continents like this can really highlight density as the main driving point. And the oceanic plate, the composition is what it's made of, right? So that will be the rocks, which in turn will be the minerals, which the crust is composed of. Now, basalt, as we discussed in our divergent plate boundary, which again is over here somewhere. So this ocean plate is being moved from its origin or starting point or area of construction, which is the mid-ocean ridge, which would be in the middle of the ocean, whether it's the Atlantic, Pacific, Indian, ridge or rise. That will be the location where the ocean plate is created, and it spreads and moves across, and then eventually it's going to hit this continental plate. So the ocean plate is made of basalt, our lovely extrusive igneous rock. All right. Now it'll be in pillars, and there'll be some gabbro down here. Okay, maybe some pyrrhotite as well. All right, which is that ultramafic rock, but mostly basalt. And again, I mentioned before, there'll be a thin layer of sedimentary rock as well on the top. Maybe it's limestone, shale, mudstone, siltstone, maybe some breccia. Basalt is the main one. Now, basalt is dark and heavy or dense, so it's going to be around 3.0 grams per centimeter cubed density of basalt, generally. Whereas if we compare it to the continent, even though it's thicker, a lot thicker, a lot more mass, all right, a lot more size to it, the continent is made mostly of granitic. Okay, let's change that a little bit. Granitic rocks. Okay, so granite, andesite, those kind of rocks. Now, even though it's a larger crust, the average density is 2.7 grams per centimeter cubed. So this is less dense than the colliding converging ocean plates. So what happens is it's the physical term of negative buoyancy. So the weight of the plate is stronger or more than the force of buoyancy. So in layman's terms, there is sinking of the denser plate, which is the ocean plate right here. So as it collides with the continental plate is pushed up a little bit of uplift there from the plate, but it's forced downward into the asthenosphere, which is that plastic, ductile kind of material or environment. And you can draw this nice big arrow going down, again, following the convection currents. So there is some sort of slab pull by the convection currents, but mostly by gravity and the density of the ocean plate, causing the movement down underneath at a certain angle underneath this larger continental plate. Okay, so this is called subduction. I'm going to put it right here. And this continental plate here is called a slab. So it's the subducting slab. All right. All right, now let's look at the ocean. So I put the ocean here. And in theory, I've put a beach and a coastline. Now, where these guys meet, so this kind of like area right here, this area right here, is called a margin. It's the transition period, transition area between the plates, whether it be ocean plate, continental plate. There's an area where it transitions between the crusts, goes from ocean to continental or different version, and we call it a margin. Now, in this case, because there is a destructive element or destructive component to this boundary, because the ocean plate is subducting, that we call this a destructive plate boundary, and we also call this an active plate margin, as opposed to a passive plate margin where the switch from ocean crust to continental crust, there's no subduction. It just is a gentle transition from different types of composition, from the basaltic to more granite. So this is active plate margin with a destructive element. Now, I mentioned that. Where is that? It is in the subduction. As this plate, so as this area of plate, let's do a little area right here. As this part of the subducting slab or the ocean plate gets forced down through negative buoyancy, it's going to sink deeper and deeper and deeper down into past the crust and into the asthenosphere, where we know because of the geotherm, it increases by average of 30 degrees Celsius every kilometer, it's going to get hotter. Now, it can go down 50 kilometers, 100 kilometers, 150 kilometers, even down as deep, some studies saying below 660 into the mesosphere, and even down to the mantle core boundary, some articles suggest. And that's thousands of kilometers down. So As it goes down deeper, you increase temperature and pressure, but you're going to increase the environment to a point where you're going to promote melting. To get hot enough and enough pressure, more the pressure than temperature, to create melting. And we'll get to this in a different video because it's quite in depth. Get it? In depth. But you get melting occur here, and the melting is going to cause magma production and decompression melting. And what you'll get is the magma is going to rise up and form volcanoes on the surface of the continents and cause these create these volcanic arcs. Now, I mentioned the ocean. This could be the Pacific, and I use that a lot. All right, it could be different parts of the Pacific. So you have the Ring of Fire, and we can also include earthquakes as well into the diagram if you want to. But volcanoes are the obvious choice for this one. So you can choose any part of the Pacific. You can choose the eastern part, western part, but the western part has the more aggressive dip angle and subduction, and it also has, because of subduction, you see this ocean floor descending deeper. So it's actually very deep, this part of the ocean continent margin where they actually meet, and we call this an ocean trench. Ocean trench. Again, the classic ones would be the trenches around Japan, around the Aleutian Islands, the Aleutian Trench. You can even discuss the Puerto Rico Trench in the Caribbean or Atlantic. You can also look at a case study of the Marianas Trench off the coast of the Philippines, which is the deepest part of the ocean. All right, the Challenger Deep, 35,000 feet down. So it is crazy deep, amazing environment, and you can do a whole thing on that as well as a case study to show the effect of subduction and what it does with the ocean and this new environment they found and how harsh it is. But you have this ocean trench, and what happens is as the plate is subducting, the ocean plate, there is friction, and there is parts of the ocean plate right here will get broken off and pushed onto and up onto the continent. And what happens is it creates what's called an accretional wedge or prism. Okay, there basically is layers of scraped off thin slices of like sedimentary rock. So there'll be sedimentary rock right here, thin slices of sedimentary rock put onto the continental crust right there, and this is called an accretional wedge. So I'm going to go into different parts of subduction, the dip angle, the production of magma through basically dehydration of the slab in different videos. Please check it out. I hope this helped with building your diagram, building this process, this amazing collision of two plates. And you can link in the mid-ocean ridges, you can link in earthquakes, you could link in the volcano production, link in the Ring of Fire, you could link in different locations, examples, the trench, even go back into your geology with the different rocks, composition of basalt, granite, and the Earth's interior with the asthenosphere and a convection current. So it really is a cool, very connected diagram for geology. All right, thanks for listening. I hope you guys enjoyed it. If you liked it, please subscribe and leave a comment.